While the textbook doesn't cover modular arithmetic or number bases explicitly, understanding these is fairly important to some of the problems that we'll encounter during the course. Since this is something that you might not have dealt with in a while, we'll devote a couple of videos to providing a little bit of a refresher. I am assuming that you've been exposed to modular arithmetic before, so there shouldn't be any new concepts here. Modular arithmetic is really just how you did division back in second or third grade before you knew about fractions or decimals. It was right after you learned that not everything can be divided evenly. For instance, 35 can't be divided evenly by 9, so how do we deal with it? Well, if all we know about are natural numbers, then we say that the answer is 3 with a remainder of 8. All modular arithmetic does is focus on that remainder. We don't care about what the quotient is, so we change a couple of names. The divisor we call the modulus, and the remainder we call the residue. Extracting the residue from a number is said to be reducing it. In math circles, the operator is usually just the word mod, though many of you will be familiar with using the percent sign as the modulus operator, since it is used as the remainder operator in a number of programming languages. All integers that share the same residue for a given modulus are said to be equivalent or congruent. So 35 mod 9 is congruent to 8. Here the word mod, followed by the modulus, is written in parentheses off to the side. It's really just a note, but a note that is needed because 35 is not always congruent to 8. It just happens to be in the case of a mod 9 world. Any value that is congruent to 0 when reduced by a particular modulus is evenly divisible by that modulus. This is a property that is often exploited. The modulus operator can be distributed inside an expression as far as we want, all the way down to the individual values and variables. But one thing we have to keep in mind is that at the end, we still need to perform one final modulus operation at the point where the mod operator was originally placed. You might ask why we might want to distribute the mod operator when we're still going to have to do it at the end anyway. The answer is that it can make the intermediate calculations much simpler and faster, either by hand or by a computer. Consider this example. We can either evaluate the entire expression and then divide the result by 17 to get the residue, something that most of us would like to avoid if having to do it by hand, or we can reduce the intermediate results mod 17 every chance we get. Just doing this to the original values in the expression immediately gets us to a much simpler equation. In fact, one that most of us can probably do in our head, or at least easily with pen and paper. But if not, we can continue applying reductions until we get to a point that we can finish it off directly. The reason that modular arithmetic is such fertile ground for the field of finite automata is that, by its nature, we only have to deal with a finite set of numbers, namely the possible residues. In any situation, we can replace one instance of an integer with any other integer that is congruent to it. We generally use the smallest non-negative such integer, and for that reason, this value, which lies within the range of 0 through the modulus -1, is known as the principal residue.